we move on to the next classification of your tanks, that is rectangular water tanks resting on ground. In the previous lecture we studied the circular tanks resting on ground. So we have covered this portion. For tanks resting on ground there are two classifications, circular and rectangular, and we have completed the circular. Now we will move on to the rectangular tanks, where we have two types of tanks based on its dimensions, L by B less than 2 or L by B ratio greater than 2. Now first of all we will look at the parts of a rectangular tank. The rectangular tank has two types of walls. One is long wall and another is short wall. There are two long walls and two short walls, and there is base slab. And like in the previous case, the top of the tank is covered with a simple lid or cover which need not to be designed. L is the length of long wall, B is the length of short wall, and H is the height of your tank wall. Now first we start with the first category, that is L by B less than 2. So I will keep on reminding and comparing the different steps or different behaviors with the previous types of tanks which we discussed, so that you have better understanding and you develop a comparison between these all side by side. So when the L by B ratio of rectangular tanks is less than 2, long walls and short wall behave in a similar way. That is, the act, whatever the structural action is, behavior long wall is showing, the same will be shown by the short wall. So what is this structural behavior? The bottom portion of long wall as well as short wall up to height h from base behaves like a cantilever with bending in vertical plane. This is similar to that of circular tank with rigid base, where the bottom portion was acting like a cantilever, with the main difference that in that case h was h by 3 or 1 meter. Here we have h by 4 or 1 meter. So the bottom part of the tank behaves like a cantilever, long wall as well as short wall, and the upper portion of the tank above this height, small h, up to the full height, undergoes continuous frame action. That is, all tank walls act together as a part of a continuous frame. So what does this continuous action means? Look at this diagram here. This is the plan of your tank. So these are the short walls and these are the long walls, and this is the pressure acting. So the top portion, unlike the circular tanks, the top cannot be considered as completely free. As you can see here, the top of this particular tank of long wall is supported on short wall, and the short wall is supported on long wall. Similarly, the long wall is supported on this short wall, and similarly here also. So we can say that all these junctions or corners behave like supports for these particular elements. So if you can see it as a continuous element, like for example, if I open it from here, if this is A, B, C and D, so I open this rectangle, so this is A, B, C, D, this is point A, B, C, D. So if we open this rectangle into a line, these A, B, C, D will behave like supports, and these AB, BC, CD and DA elements will behave like continuous beam. So this is the continuous frame action. So it is quite simple. The bottom portion will act as cantilever and the upper portion will together act as a continuous beam. So as you can see here due to this water pressure there will be vertical bending, and here due to this water pressure there will be horizontal bending, because if you see here, this type of load will lead to, if this is the water pressure acting on this wall, so this will be the bending, so this is the horizontal bending, and similarly here this will be the horizontal bending in short wall. Here I have made this like this because sagging will be in the middle portion and hogging will be near the supports, as this is the continuous beam or continuous slab. So the reinforcement in the bottom portion will be due to the vertical reinforcement due to cantilever action, and reinforcement in the upper portion will be the horizontal reinforcement due to the continuous frame action in the upper portion, that is H minus H. So now we will learn both how to calculate the moments and forces due to this cantilever action and this continuous frame action in this type of tank wall. So this is quite simple. First we will take the continuous frame action. The continuous frame action acts in the upper portion, that is at a height of h minus h from top. So first let me make you understand that what we are doing in this particular case. So I am making this this is tank PQRS, plan of this tank. So I am making this long wall PQ here. So this is your wall and this is the force acting on this wall. So we have understood now that the P and Q will act as continuous supports for this particular element PQ. Now due to this load, the bending will be horizontal bending like this, and as these are continuous supports, there will be negative moments or hogging here, and there will be positive moment or sagging here. So this will be sagging positive moment, hogging negative moment. So the reinforcement will be provided like this here, like this here, and like this here. So what are we what will we want to calculate here? We want to calculate first this positive moment acting at the center and these negative moments acting at the corner. But as it is a continuous slab, there will be a short wall act here also. So some of the moments of this short wall will get distributed to this end, and some of the moment of this long wall will distribute to this short wall. Similarly for the other corners also this will happen. So what we will do for the corner moments, there will be some fixed end moments due to this load. I will make this here again. If this is a continuous beam, okay, let me remake this. If this is a continuous beam PQ, this is a beam PQ, and this is another beam PS. So this is the continuous support, middle support. So what happen is, due to this load and this water pressure here and this water pressure here, some fixed end moments will act at this end, and due to this load some fixed end moment will act at this end. So you know from structural analysis that what are fixed end moments and what are the center moments. So these fixed end moments will act near the support of element PQ and PS, and this will be different for both these beams because the length of these beams will be different. So what happens, here we have one fixed end moment, here we have another fixed end moment. This is a common joint here. So what we do in this case, we calculate the moment at this common junction or corner by using the moment distribution method. So now I will be explaining you here what we are doing. So first we will calculate the moments due to continuous pressure, frame. So what is the pressure acting here? In the previous case also, for circular tanks with rigid base, the pressure due to water was maximum at a height of h minus h. So P is equal to gamma h minus h. This is the water pressure. So this is the load acting or the pressure acting on the walls. Now we will first calculate the bending moment and corner, like I have shown you here. This is the corner, this is one corner, this is the second corner. So we will first calculate the bending moment at corners, and then we will calculate the bending moment at the center. So first, for calculation of bending moment at corner, we will calculate the fixed end moments at corners of tank. So fixed end moment along short wall MFSW, if we consider this particular short wall PS, the fixed end moment due to this load at this one support, like this support, will be PB square by 12, and at this support also it will be PB square by 12. Or if you consider the short wall QR, here it will be PB square by 12 here, and for long wall it will be PL square by 12. So I will be taking only one corner, similar action will be done on the different corners. So this is the fixed end moment due to this pressure PB square by 12, and this is the fixed end moment in the long wall PL square by 12. So we have calculated the fixed end moments. Now look at this junction. This is PQ part of the continuous frame, this is the QR part of continuous frame. This is the fixed end moment at during long wall and short wall near the corner Q. Note here that this fixed end moment is not acting exactly at the corner but near the corner in PQ element, and this is acting at the QR element. So now what we need is the common moment acting at this common joint Q. So for that we will be using the moment distribution method. So how you do the calculation by moment distribution method? We have moment MFLW and MFSW, that is fixed end moments in long wall and short wall. So we calculate first of all we calculate distribution factor in PQ beam and QR beam. Distribution factor is calculated on the basis of stiffness of both these elements. So now first of all we calculate the stiffness of both these walls, then we calculate the distribution factor, and then we distribute the moments by moment distribution method and get one common moment M corner. I will explain you the calculation in the design problem, which I will discuss later. So here first thing we get is the moment at the corner. So now we have achieved what we wanted, that is the common corner moment at this end Q or any of the corner. Now we have got the VM at corner. Now we will calculate the bending moment at the center of wall. Bending moment at center of the long wall will be PL square by 8 minus moment at corner, which we get from here, and bending moment at center of short wall will be M center PB square by 8 minus M corner. So as you can see here, as we are calculating, if this is a long wall, we are calculating the moment in the central portion due to this particular load. So as this is center, so we don't need to use any moment distribution method because we will get only one value here. So we just get moment at center of the long wall. Now we calculate the thickness of wall. Now this is very important. Now let me take you back to the previous lectures. For circular tank with flexible base, the thickness of wall was calculated on the basis of the principle that sigma T is less than sigma Ct. For the circular tanks with rigid base, the thickness of wall was calculated on the basis of the maximum cantilever moment at the base of wall. Now here, for rectangular tanks with L by B less than 2, the thickness of tank wall is calculated on the basis of the moment at corner. This is the most critical moment for this case. So M at corner. So the thickness of tank will be calculated by D is equal to under root M corner upon RB. This is the effective thickness, and the total thickness will be effective thickness plus effective cover. So note here, I am putting the star here so that you can remember this point, how the thickness of wall is calculated for this case. Now we have calculated the moment at corner and moment at the center of your long wall as well as short wall. But now another phenomena is occurring here. Look at it closely. We got the positive moment at this particular center of the long wall or short wall due to this load. Now there is another force acting in this particular long wall, that is T. Now what happens due to this T force? There is another moment acting at the center, that is T into this particular distance. And what is this distance? This distance is basically, if the reinforcement for positive moment is provided here, then T is into this X, where X is the distance between the T force. This T force acts at the center of the wall, and this is the cover, and improperly in the next slide. So what I want to make you learn here is that the moments which we have calculated here will be reduced due to this moment in the opposite direction, that is T into X, due to the direct hoop tension acting in the direction of your long wall or short wall. So we will calculate some modified bending moment. So the moment at corner we got from the previous slide here from moment distribution method. Now this moment will further get reduced due to this moment t into x. Similarly, moment at center will also get reduced by an equal amount. So what is T here? T is the direct tension in long wall, which will be gamma h minus h into b by 2. Note here that for direct tension in long wall it will be multiplied by b, and for short wall it will be multiplied by L, that is the length of long wall. So T is this, I will write here TL, and x is the distance between the line of action of tensile force and the point where we are calculating the moment. As we are calculating these corner moments and the central moment at the location of your reinforcement, because ultimately the reinforcement will be provided at these particular areas. So this is the x distance, this is the effective cover where we are providing the reinforcement, and this is the x. So x will be, if the thickness of the tank is t, x will be t by 2 minus c dash. So we can get the modified design corner moment for long wall as m corner minus TL into x, and for short wall m corner minus TB into x. The m corner will be same for long wall and short wall, as the corner is common for both of those. So the TB here will be, for short wall, TB will be gamma h minus h L by 2, and the TL will be gamma h minus h into b by 2. Now similarly we calculate the design moment at center. The design modified bending moment at center or midspan will be the moment at center of long wall minus T into x. We have calculated the moment at center of long wall by this formula. So this will further reduce by minus T into x, and this will also reduce by minus T. This will be TB into x, and this will be TL into x. So this is quite simple. The design bending moment at the center of long wall will be m center long wall minus the TL into x, and this is, sorry, not b but TB into x, where TL and TB are written here. So finally we will be using these moments, that is design bending moment at corner of long wall, design bending moment at corner of short wall, design bending moment at center of long wall, and design bending moment at center of short wall. So we will provide reinforcements due to these moments. So calculation of reinforcement will be like this. So reinforcement due to moments, calculation of reinforcement will be reinforcement due to moment and reinforcement due to direct tension also. As T is also acting in these walls, so reinforcement for that AST will be T upon sigma ST, and bending moments are also acting on the walls, so reinforcement due to that will be M sigma ST into JD. So we can say that if we are calculating the reinforcement due to moment at corner, then it will be the sum of reinforcement due to moment at corner plus reinforcement due to direct tension, and total reinforcement will be reinforcement at corner on the inner face, and reinforcement due to moment at center plus reinforcement due to direct tension will be the reinforcement at center and outer face. Why inner and outer face? Because due to, if we take any wall, either short wall or long wall, if this we are taking short wall and this is the water pressure, now what will be the behavior? Like this. So at corner we will provide, as the hogging is happening, so at corners we will provide reinforcement at inner face, and in the center we are providing reinforcement at the outer face. So this will be the plan of tank wall. This is reinforcement due to moment at corner, moment and tension at corner, reinforcement due to moment and tension at corner, reinforcement due to moment and tension at center. Now I have summarized this all here. So reinforcement in long wall will be reinforcement in corner and reinforcement in center of long wall. Reinforcement in corner of long wall will be reinforcement for design moment at corner, which is MD corner LW upon sigma STJD. Now note here we will be using these values here, which we calculated after modifying. So MD corner of LW long wall upon sigma STJD will give you the design moment at corner. And at corner direct tension is also acting, so the reinforcement due to direct tension will be T upon sigma ST. So the total AST at corner of long wall will be this plus this, and this will be at corner on the inner face. So if I draw a diagram here, this is the short wall and this is the pressure. So this is the corner reinforcement here and here, which is the sum of AST1 plus AST2. Similarly, reinforcement in center of long wall will be calculated on the basis of design moment at center plus tension at center. So design moment at center we have calculated here. So design moment at center will be reinforcement at center due to moment will be moment at center of long wall upon sigma STJD plus reinforcement due to direct tension at center plus these both values will be same, as T will be same in corner as well as the center. So we add both these reinforcement to get the reinforcement at the center of your long wall, and this will be provided on the outer face due to sagging of outer face and tension on the outer face. Similarly for short wall, this also is same thing is happening, just we will be using the moments and tensions for short wall. MD corner of short wall, this is TB, MD center of short wall, TB, and we get all these reinforcements. Now when we get these reinforcement, 4 types of reinforcement, 2 in long wall and 2 in short wall, then we assume that individually the diameters of these reinforcements and calculate the spacings. We do not assume diameter here or here and then add, that will be very confusing. So we first add the reinforcements and then we calculate the spacing. So this was all about the continuous frame action. The cantilever action reinforcement will be same as that in the case of circular slab with rigid base. The cantilever action is acting at a height of small h, which is either h by 4 or 1 meter. So the moment force due to the water pressure will be half gamma h into small h, and moment will be into h by 3. So the reinforcement will be M cantilever upon sigma STJD, and this is provided on the inner face or water face, because as I have explained to you many times before, due to this water pressure the tension will on this cantilever will be on the inner face. Now the design of base slab will be done same, minimum reinforcement and minimum thickness as provided. Now what are the main important points for tanks with L by B less than 2? The main reinforcement is the horizontal reinforcement due to continuous frame action at center and corner of long wall and short wall, and the vertical reinforcement is due to the cantilever action on the inner face, and thickness of tank wall is decided on the basis of the moment at corner. So this is the rectangular tanks with L by B less than 2. Now we will look at a design problem. Here we have to design a rectangular water tank having length 6 meter, width 4 meter, depth 3.5 meter, M25 and Fe 4.5. So the first step will be same, calculate the design constants K, J, R like this by taking the values of permissible stresses from IS 3370 part 2. Now first of all we decide the type of tank. As this is a rectangular tank, we calculate the L by B ratio. So it is coming out to be 1.5, which is less than 2. Hence you have to ascertain at the first step that which type of structural behavior the walls will be showing. So as L by B is less than 2, both long wall and short wall will behave as cantilever up to h height, and above that as a continuous frame. So what is h here? 3.5 by 4 or 1 meter, whichever is more, h by 4. So it is coming out to be 1 meter. So up to height 1 meter, the tank will act as a cantilever, and above that continuous frame. So first we will calculate we will do the continuous frame action. So water pressure at height h will be gamma into h minus h, which is coming out to be 25 kilonewton per meter square. So this is the plan of the tank. These are the long wall, these are the short walls, and this is the water pressure. Now first of all we calculate the fixed end moments at the corner of long wall and short wall, near the corners, not at the corners. So fixed end moment in the long wall will be PL square by 12, and fixed end moment in the short wall will be PB square by 12. So we get these two values of fixed end moments. Now what we do, we have to find out the value of corner moment at this particular common junction of long wall and short wall by moment distribution method. So how we will do it, we will consider it to be we will open this is P, and this is Q, and this is R. This is long wall and this is short wall. We have fixed end moment here and here, and this is the common joint where we have to find the moment. So this is the case. So for that we have to calculate the distribution factors first. So stiffness of long wall, for walls the stiffness is assumed to be 4EI by L, 4EI by whatever the length of the wall. So stiffness of long wall will be 4EI by L, hence we get it to be 2 by 3 EI. Stiffness of short wall is 4EI by length of short wall, which we get is EI. Distribution factor is, if you remember, the stiffness in that particular portion divided by total stiffness. So stiffness distribution factor for long wall will be stiffness in long wall upon total stiffness, and the distribution factor for short wall will be stiffness in short wall upon total stiffness. So we get the distribution factors to be 0.4 and 0.6. Now the fixed end moment at this point is here, you can see 75 for long wall, and for short wall is 33.3. So if you remember moment distribution method, what do? We first of all find the balance moment, whatever is acting here. So the balance moment will be 75 minus 75 plus 33.33, which is coming out to be 41.67. Now we will counterbalance this moment, we will counteract this balance moment by adding the same amount of moment here. So we will get these two values. Sorry, this is negative sign here. So if this is negative, we will add an equal amount of positive 41.67 here. Now this moment is distributed in both these long wall and short wall in the ratio of its distribution factor. So always remember this, that whatever balance moment you are adding, the sign of that is very important. If this is negative, you have to counterbalance with positive, and if this is positive, this will also come out to be positive. So 0.4 times of 41.67 will be the distributed moment in long wall, and 0.6 times of 41.7 will be distribution moment in short wall, and we add both these, minus 75 plus 16.66, and we add both these, 33 plus 25, to get the moment at corner. So we continue the moment distribution method till we get the same value here. So we have got this in the first step only. So this is the common moment at corner, 58.33. We have determined the moment at corner of this tank walls. So now we will use this corner moment to calculate the thickness required of the wall, as this will be the most critical moment. So the D, that is effective depth required to carry this corner moment, will be D equal to M corner upon RB. So here we are getting small d, that is effective depth, as 195 mm. So we provide total thickness a bit higher, that is 250 mm with effective cover of 40 mm. So we get the final effective thickness as 210 mm. Now we calculate the design bending moments in corner and center of long wall and short wall. I have calculated these in this form of table so that there is a better understanding and you can understand the steps together. So for long wall, first we calculate the direct tension, which is gamma h minus small h into b by 2, and for short wall, gamma h minus h into l by 2. So we are getting TL this and TB this. So the the moment at corner was 58.33 as we got in the previous step. Now it will get further reduced due to the moment due to the tension in the opposite direction. So M corner minus TLX will give you the moment, designed or modified moment at the corner of long wall, where X is this distance, that is distance between the line of action of T and the center of reinforcement. So this will come out to be thickness of the wall divided by 2 minus the effective cover 40 mm, which is 85. So we get the design bending moment at corner of long wall as moment at corner minus TL into X. So we get this value. Similarly, we get the moment at the corner of short wall, design moment, by deducting the moment at corner of short wall, which is the same 58.33 minus TB into X. So this is the second moment at corner of short wall. Now for the center of long wall, the moment at the center of long wall will be PL square by 8 minus M corner. This is the expression. And the design or modified bending moment at center of long wall will be determined by deducting TL into X from this. So you can do this in the same step also, you can deduct it here also, but I have done here separately so that you can get a better understanding why we are doing this. So bending moment at center of long wall is this, and design bending or modified bending moment at center of long wall will be minus TL into X. So we get this value. Similarly for short wall, bending moment at center of short wall will be PB square upon 8 minus M corner, and the modified will be minus TB into X. So we get this value. So hence we get total 4 moments, final moments, that is design moment at corner of long wall, design moment at corner of short wall, design moment at center of long wall, and design moment at center of short wall. Now we calculate the reinforcements due to these design bending moments. So this also I have calculated in the form of table. So first we calculate reinforcement in long wall at corner and at corner for short wall. So the reinforcement at corner of long wall will be due to the moment at corner as well as the tension at corner. So the moment at corner is MD corner LW. So AST will be MD corner LW divided by sigma STJD. And the area of reinforcement due to tension at corner will be TL upon sigma ST. So we calculate both these reinforcements and we combine both these to get the total corner reinforcement in the long wall. Similarly, the same is done for short wall. Here we use the design bending moment at corner of short wall, which we calculated in the previous step. So we get AST corner at short wall, then reinforcement at center of long wall and reinforcement at center of short wall. Here AST will be MD, design bending moment at center of long wall, upon sigma STJD, and AST2 will be design bending moment, reinforcement due to tension at center, which will be the same 384. So we get 4 reinforcements, that is reinforcement at corner of long wall, at corner of long wall, at corner of short wall, center of long wall, and center of short wall. So corner reinforcements will be provided at the inner face of long wall and short wall, and the center reinforcement will be provided at the outer face of long wall and short wall. So what we do now that we have calculated the reinforcement values, we assume the diameter of bar and calculate the spacing of each type of reinforcement. So these are the total reinforcements which we have got. I have summarized it here. So the AST minimum will be 0.35%. I have calculated it here only so that we can compare it later on. So AST minimum will be 1000 into 250 to the cross sectional area of your tank wall into 0.35 upon 100. so we are getting it to be 875. So keep this in mind. We will always check that the reinforcement should be greater than AST minimum. So here at centers we get positive bending moment, and at the corners we get the negative bending moments. Now the AST at corner of long wall was this, so we assume diameter of bar and calculate the spacing. So here we are getting it 116, so we provide 20 mm dia bars at 100 mm center to center on the inner face of corner. Why inner face? Because the inner face of the, because if this is the long wall and this is the load pressure due to water, so due to this load this type of bending will occur. So here at corner we have negative bending moments, so we are providing at this reinforcement at the inner face, and the positive at center, the positive reinforcement will be provided at the outer face. So AST center was this, we assume diameter of bar, calculate spacing, and we get 20 mm dia at 120 on the outer face. Similarly we do it for short wall. Now look here, for AST at the center of short wall it is coming out to be 660, which is less than the minimum AST, so we adopt minimum AST. In all other cases the AST was greater than AST minimum. This was also greater, this is also greater, and this is also greater. So we get the spacing to be higher. So using 20 mm dia bars we get 300 mm spacing on the outer face of short wall because it is less reinforcement. So we have got all types of reinforcement. Now we look at how these reinforcements will be placed. So first we start from the corner. First I am taking the detailing of the long wall. So the reinforcement at corner will be provided in the long wall. So this was coming out to be, you can check, 25 at 110 in the long wall. So this will be provided on the inner face. If this is the plan of your long wall and this is the inner face and this is outer face and this is the load, I have shown the inner face with the help of load acting due to the water pressure. So this is the reinforcement near the corners, here and here, 20 diameter at 110 center to center. Next type of reinforcement is the center reinforcement. So you can see in the central portion the bending moment will be on the sagging on the outer side, so we provide the reinforcement on the outer face like this in the central portion. So these are the main reinforcements in the long wall. Now you can see I have put reinforcement here also. As we know, from safety point of view, we should not keep any point empty. So we can, although the reinforcement is not required on the outer face at corners and reinforcement is not required on the inner face at the center theoretically, but some of the reinforcement can be provided. So what do? We just extend this reinforcement towards the center and extend this reinforcement towards the corners, but not all the reinforcement, only the alternate reinforcement. So this type of reinforcement will look from the elevations. Consider this is the elevation of your front elevation of your long wall, and this is the outer face. So in the outer face the main reinforcement is concentrated in the center, as you can see. So here we are providing reinforcement in the central portion and extending alternate reinforcement towards the corner, as you can see, because so that a minimum amount of reinforcement is also provided on the inner portion of your on the corner portion of your outer face. So as you can see, in the central portion we have large amount of spacing, that is 25 at 120. This spacing is 120, and on the and we are extending this reinforcement alternatively, so the spacing will be doubled, that is 240. So this reinforcement is this. and this long reinforcement is this. So these are the reinforcement on the outer face. Similarly on the inner face, in the inner face the main reinforcement is at the corners, this and this at the corners. But as explained earlier, we should not keep this portion empty, so alternate reinforcement is extended towards the center also. So we provide 1 bar of full length and 2 bars of length limited to corner portions only. So hence this spacing will be 20 diameter at 110 and this spacing will be double 20 diameter at 220. I hope it is clear to you how this will look like. Similarly for the short wall also, in short wall we have reinforcement in corner 25 at 110 and at center we have 25 at 300. So here you can see I have provided only 1 bar and not 2 types of reinforcement like in central portion and in the corner portion. This is because as this reinforcement is already quite less, 20 diameter at 300 center to center is quite large spacing. So if we alternatively this is the actual reinforcement, main reinforcement. So if we double this reinforcement near the corners, then it will come out to be 600, which is very less, very large, sorry. Hence we provide the reinforcement in all the length of the short wall or the outer face. I will repeat, although the reinforcement is required only in the center of outer face, but as this reinforcement is quite less, if we provide one reinforcement like this and one reinforcement like this, one like this, so this spacing will come out to be 300 because it has been calculated at 300, but this in the next spacing this will come out to be 600, which is too large. So we should not provide such large spacing in any RCC element. So what we do, we just provide whole length reinforcement. If this reinforcement was not so less, 300 center to center spacing means less reinforcement, then we would have also done as in the case of long ball. For the inner face, the reinforcement is like this. This is 20 diameter at 110 and this will be 20 diameter at 220. So I hope the detailing of long ball as well as short ball is clear to you. Now this is the horizontal main reinforcement due to continuous frame action. Now the cantilever bending moment will be calculated like this. This is coming out to be 5.83 kilonewton meter, and the reinforcement due to this will be provided on the inner face of your short wall as well as long wall. So now the AST will be M cantilever upon sigma STJD. Now here D is, if you look here closely, we have already provided the horizontal reinforcement in the previous case of 20 mm diameter. Now this is the horizontal reinforcement. If this is the cross section of a wall, this is the horizontal reinforcement, these circular points, and this is the vertical reinforcement. If I enlarge it here, this is the horizontal reinforcement and this is the vertical reinforcement. So for this vertical reinforcement, what is D, effective depth? This is the total depth of your tank wall minus this total distance. If this is the tank wall, this is the horizontal reinforcement provided like this, and this is the vertical reinforcement which will be having some diameter. So D for this vertical reinforcement will be effective depth, this total depth, effective depth for this vertical reinforcement will be total depth minus effective cover for this reinforcement, and that will come out to be the total thickness is 250 and effective cover for this reinforcement, that is up to the central point of this reinforcement, was 40. So minus 40 minus this diameter of bar was 20, so 20 by 2, And if we take this diameter of bar also 20, then this will be the center of this vertical bar will also come out to be 20/2. So we get D dash to be 190 mm. So the AST due to this cantilever moment is coming out to be 274, which is less than 875 minimum AST. So if we provide AST is equal to minimum 875. Now as this is a tank wall, here we will provide the vertical reinforcement on the inner face, which is coming out to be the minimum reinforcement. But some reinforcement can also be provided on the outer face just for safety. So this is also minimum reinforcement and this is also minimum reinforcement. We have calculated this inner face reinforcement to be minimum reinforcement here. So what we do, we divide this reinforcement equally on both parts. So this is half surface zone here, half surface zone here. So provide half on each face of wall. So providing 437 mm square on each face. So we use the diameter of bar, calculate the spacing, and we find out the vertical reinforcement as 10 mm dia bars at 180 mm center to center on both the faces of wall. This is same for long wall as well as short wall. Now finally the base slab is designed as before. Calculate AST minimum for base slab and provide this reinforcement equally on both directions on each face of your base slab. So this is the reinforced detailing of your tank. Now this is the summary which you have to make for each type of detailing. This is long wall. In long wall we had corner reinforcement here and on the inner face, and center reinforcement this, and these center reinforcement was extended towards corners and corner reinforcement was extended towards the center. In short wall, this was the corner reinforcement, this was the corner reinforcement, and this was the extended reinforcement. And in the short wall, in the outer face, whole of this reinforcement was provided on the outer face together, because it was coming out to be very less, that is 20 diameter at 300 spacing. So this is the plan of your tank, and the section of the tank will look like this. So in the plan of the tank, if you look at here, these dots show the vertical reinforcement, which is 10 diameter, I think we have provided it to be 20 diameter at 10 mm dia bars at 220 mm center to center. I think I have written here incorrectly. This will be 10 diameter, I think. Let me check. Yes, 10 mm diameter. So this is the reinforcement here. Now we look at the section. If we cut the section of this long wall here at this particular point, we cut the section here. So in the inner face we will get this reinforcement, that is 20 diameter at 110, and in the outer face we will get the extended reinforcement, that is 20 diameter at 240. So this is very important, that where you are cutting the section. If we cut the section here, the reinforcement on the inner face will be 25 at 220, and on the outer face will be 25 at 120. So it is very important to mention where you are cutting the section. So I am cutting the section at AA of the long wall. So the outer face is having the horizontal ties, horizontal reinforcement is provided on the outer face. So if you look at this section, this is 20 diameter at 240. So these reinforcement, if you look from here and you cut the section, it will look like these dots. So 20 diameter at 240, and the inner reinforcement, horizontal reinforcement, is 20 diameter at 110 center to center, and the vertical reinforcement is 10 mm diameter at 180. I think I have again, let me check, 10 mm diameter at 180. Yes, this is 180 mm center to center. So these are the vertical reinforcements which are provided same on inner as well as outer face. Now this is the base slab section. The base slab section, we have same reinforcement in all directions and all faces, that is 10 mm diameter bar at 220 mm center to center. So similarly, whenever you draw whenever you complete the design of tank, rectangular tank, first of all draw the plan of tank showing reinforcement in one long wall and one short wall. You don't need to show the reinforcements in all the on 4 sides. You can, but you can show on 2 sides only. And draw one section of long wall and one section of short wall. Here I have drawn only the section of the long wall at this point. You can draw the section of short wall also at any point you require. So at least three drawings are necessary. First is the plan of tank, then is long wall section and short wall section. So similarly, short wall section can also be made if we cut the section of short wall at the center. In the outer face we will have 20 diameter at 300, and in the inner face we will have 20 diameter at 220. So this is the detailing of your RCC rectangular water tank. Here you can see this is 20 diameter at 300 center to center on the outer face, and 20 diameter at 220 on the inner face. If you cut the section here, outer face you have same 25 at 300, and inner face you have 25 at 110. And vertical reinforcement I have not shown. It will be same as shown here. So this is the whole detailing of your tank.